Good afternoon, this is Stanley Forster for IRSC Physics. We're doing Chapter 11, Fluids now. Okay, some definitions first. We're going to talk about density. Okay, density, as we're going to be using it in this chapter, is mass per unit volume, the amount of stuff per unit volume. Okay, if we talk about the density, which weighs more, the old joke, which weighs more, a pound of feathers or a pound of lead? Well, a pound is weight. So a pound is a pound. They weigh the same. But if you take a look at the size of a pound of lead and the size of a container that contains a pound of feathers, you may be very surprised. The pound of feathers was a low density. So therefore, to get a full pound of feathers, you may be required to have a very large container. Okay, units are kilograms over meters cubed. Also, well, it's the only units of mass in all we're going to use. Okay, pressure. We know pressure. You know, PSI, pounds per square inch. Okay, this is force, pounds force. Remember, with the weight force is a force. Okay, so pounds per square inch. Okay, force over area. We can also do, let's say, newtons over meters squared. Okay, that's actually a unit called a Pascal. And to a rough approximation, an atmospheric pressure at sea level is about 10,000 Pascal. 1 times 10 to the 5th Pascal. There's a more precise definition, but there you go. Okay? A little bit about this. If we take and multiply the top and the bottom by a length, okay, we can do length divided by length cancels out, so it's just 1, right? Length over length is 1. We can always do that. So force times a perpendicular length, that's work. That's energy. That's going to be measured in joules. Okay? And area times a perpendicular length, that's going to be a volume. Okay, so this is energy over volume. So pressure is not just force per unit area, but it's also an energy density. And as we go through this, we're going to see that we have expressions that can be interpreted as a kinetic energy density and as a potential energy density. Okay, and so a lot of the same thought process we use for our energy balances, we can use for fluids. Okay, big thing here, pressure at a depth in a static fluid. Okay, static meaning it's not moving anywhere. If it is moving, we'd have to put a velocity term in. Okay, so pressure 2 is just pressure 1 plus this modifying term, rho GH. Okay, rho is again density, mass per unit volume. H is the depth, the difference between where you're measuring pressure 1 and pressure 2, and G is the gravitational constant. Okay, so let's take a look at that. Rho GH, mass per unit volume, that's your density. Okay, so on the top of this fraction, we have mgh. That is a potential energy, okay, over volume. So this is your potential energy term. Again, we have energy per unit volume. Okay. All right, here's an example. Pressure 1 is 0. Let's just take the surface of a body of water as 0, okay? We know it's atmospheric, but we're talking about a difference in scalars, so we can set an arbitrary 0 anywhere we want, just like with temperature. You can set temperature at the freezing point of water for Celsius, or you can set 0 at much below the freezing point of water. Well, in any case, pressure 1 is 0. Rho, which is our density, is 1,000 kilograms per meter cubed. Okay, and the height difference is 10 meters. Of course, G is 9.8 meters per second squared. So let's plug in all. Okay, so here's pressure 2 equals pressure 1 times we're going to multiply these 3 quantities here together, pressure 1. And our 3 quantities, we're going to multiply them together. And we're going to get about 100,000. We round it up. It's about 100,000 pascals, okay? Now, this is very, very close to 1 atmosphere, okay? And there's your rule of thumb. Every 10 meters you go down, you're going to gain about 1 atmosphere of pressure, okay? Now, if you're in seawater, okay, I was a little concerned about that. I had to pause for a moment and think about it because this didn't quite work out right from my memory. The density of seawater, I was in the Navy, by the way, the density of seawater is more than the density of fresh water, which is what is used here in the example, okay? And so this is, for seawater, this is going to be a whole lot closer to 1 atmosphere. Okay. Pascal's principle. Okay, this is the principle that lets hydraulics use. Okay, so any change in pressure applied to a completely enclosed fluid is transmitted undiminished to all parts of the fluid in the enclosing walls. Okay, so if we have two elements that are at the same height, okay, so this is just pressure 1 equals pressure 2. Okay, there is no potential energy term. Okay, let's go back one. This term right here, this rho GH, is not present. Okay, so pressure 1 equals pressure 2. Oh, now pressure 1 is just force 1 over area 1, force 2 over, and pressure 2 is force 2 over area 2. We can solve that for force 2. So we're going to press down with some amount of force on area 1, and area, we're going to measure area 2, but we're curious about what the upward force is, the perpendicular force is, F2. Let's see if we can figure that out. So F1 is 100 newtons, area 1 is 1/10 of a meter squared, area 2 is 2 meters squared. Okay, area 1 over area 2, you can multiply that out, that's 20. Okay, and so F2 is going to be 20 times 100 newtons, or 2,000 newtons. And that's basically the principle behind how a hydraulic system works. Okay, Archimedes' principle. Okay, this is why things float. This is why things float. The magnitude of the buoyant force is equal to the weight of the fluid displaced. All right, now if we come back, let's talk about, just think of a cube that's in the bottom of the water. Okay, not an imaginary cube, but an actual cube. Okay, and let's say it's a 1 meter cube of lead. 1 meter cube of lead is denser than water. Okay, but the buoyant force that's going to be felt on that, it's 1 meter cubed, and so for fresh water at least, it's going to experience, let's see, the density is 1,000 kilograms per meter cubed. We gave you that already, times G, so that'd be 9,800 newtons upward. Okay, that's subtracted from, okay, the gravitational force is pulling down on the lead itself, but that weight downward, the net force downward on that, is going to be moderated by a buoyant force upward. Now, let's say we have a 1 meter cube box of air. We're just going to call that negligible, compared to water, we're going to call that negligible density. Okay, and so the entire, there is a negligible weight force acting downward on this cube of air. All right, the buoyant force, however, is going to be the weight of the fluid displaced. Now, 1 cubic meter of air is again going to be 9,800 newtons, but it's going to be pointed upwards. Okay, and so that box full of air is going to experience a buoyant force that's going to shoot it straight to the surface. Okay, let's talk about how we model. Okay, steady flow. The velocity of fluid particles at any point is constant as time passes. As a matter of fact, you can think of this as the water isn't moving at all, and you're walking past it. Now, you're the center of the coordinate system, and so you would say the whole body has a velocity, and they're all the same, and they're going behind you. As you're walking forward, the whole thing is passing behind you. Okay. Unsteady flow. The velocity of the fluid particles at a point changes as time passes. Okay. Remember, velocity, that could be direction, it could be speed, either one. If, for steady flow, the fluid particles, the velocity is constant, it's not changing in speed, it's not changing in direction. Turbulent flow. It's a stream kind of unsteady flow, which the velocity of the fluid particles at a point change it radically, both in magnitude and direction, and they change from point to point. 2 points very close to each other could have very different flow. All right, let's take a look at this. Here are these streamlines. Okay, streamlines. Okay, well, these are basically this was a fog that would glow under a black light. Okay, and they have a bank of them, and then release it over from a pole that's inside the wind tunnel, and they take a good picture. Okay, and so we can see how the air moves. Okay, it's all steady when you at the front of the vehicle. Then when you get to the vehicle itself, the direction begins to change as one of the streams begins to hit the hood that pushes the rest up. Okay, so we're now in we've left steady flow. Okay, we have less steady flow. All right. And everything's kind of like moving around the vehicle. Okay, again, the direction's changing, so this is not constant velocity. Now, right off the back windshield, we can see that we have something that's called turbulent flow. All right. And it's unsteady from place to place. In fact, the luminescent color actually shows up as a different color at that point. All right. And now we have, on the bottom, we have the same thing going for a less aerodynamic object, which is just a box, and we can see the turbulent flow for this is a much bigger component of the flow. Okay, flow can be compressible or incompressible. Most liquids are nearly incompressible. There are some fluids which are compressible. Those are gases. Okay. Fluid flow can be viscous or non-viscous. This just means that there are internal frictional forces, okay? Like honey is very viscous, okay? It pours very, very slowly. Alcohol, for instance, does not. Okay? It's even less viscous than water is. Okay, incompressible, non-viscous fluid is called an ideal fluid. It means basically we can ignore changes in density, we can ignore changes in, and we're not going to experience any changes in temperature because there's no frictional heating there. We talked a bit about streamlines. This is a way of idealizing the trajectories of fluid particles. Here's a fluid particle, particle 1, 2, and 3. They're all following the same path. They're just slightly separated at a time. But particle 3 will end up where particle 1 is at some later point. And that line that connects that path just means that the velocity is parallel to that path at all points. Okay. Here's your equation of continuity. Okay, this is mass flow rate. We talk about how much fluid, you take a kilogram of fluid and you push it in one end of the pipe, you're going to get a kilogram of fluid out the other end of the pipe, okay, because they're incompressible. All right. So, mass flow rate. Okay, so we have area times the speed. Okay, so this is, so area, which is 2 units of length, speed, which is length over time. Okay, 3 units of length gives us a volume over time. Okay, density is kilograms over volume. The volume is going to cancel out, and so we're going to be left with kilograms per second. All right, and all that means here is that whatever the density is at location 1, the cross-sectional area at location 1 is, and the velocity at location 1 is going to be the same as the product of all 3 of those quantities at some later point. Okay, so this is mass flow rate, and we would use this if the density were changing, like for instance a gas through a pipe. Okay. For an incompressible fluid like water, we know the density isn't going to change, so we can just divide that out. All right. And so we now have area times velocity, or area times speed, excuse me, because we don't have a directional component in there. Area times speed, because this is area times a length over time, perpendicular length over time. So we've got a volume per second. All right, this is a volume flow rate called Q. Q is area times volume. And all that means is that, let's say we have this pipe here with changing diameter. Whatever the cross-sectional area is, that velocity is going to have a particle move through some perpendicular distance, and some volume is going to be covered in that time, whatever characteristic unit of time we're talking about. Over here we have a much smaller cross-section. In order for that volume to remain the same, in other words, that length is going to have to be velocity 1 times whatever your characteristic length of time is. Okay? And these 2 volumes are going to be equal to one another. So when your area shrinks, your velocity has to go up, which is something you know. If you've ever played with a garden hose and put your thumb over the nozzle, okay, you reduce the flow area and the flow sped up. Okay, again, this is for constant density, liquids, water, so on and so forth. Okay. Here's an example. Area 1 is 1 meter squared. Area 2 is 0.25 meters. Okay. Velocity 1 is 20 meters per second. Oh, and let's see, the area has been reduced by a factor of 4. So what do we expect the velocity to do? We expect it to be increased by a factor of 4. Okay, okay, here's Bernoulli's equation. All right, if we take the center term out, this 1/2 rho v squared, okay, that's just, and set one of your elevations to 0. Okay, this is just that pressure equation, pressure at depth equation. So that's just one way of remembering this. Now remember, what we have here is we have an energy density, some existing energy density. Remember rho GV, rho G Y, or your y coordinate, or h. You could have called this height before. Okay, height difference. That's a potential energy term. Okay, so what we're having is the potential energy term at point 1, and we're comparing that to the potential energy at point 2. Some scalar, just scalar that exists there on the gauge, and then 1/2 rho v squared. What could that be? Does that look like anything? Remember, we're talking about mass per volume. Think about this. 1/2 mass times velocity squared. This is a kinetic energy term. It's a kinetic energy density. Okay, and that means that the sum of all your various energies at some point in your system, let's say this system here now suddenly had a drop, so that this nozzle is now way down here, so that we now have a change in height. Okay, that's equation here. Bernoulli's equation is going to allow you to exercise that. Okay, so let's talk about Bernoulli's equation for with just the kinetic energy term, the kinetic energy density. Okay, if we talk about a piece of paper here, all right, the vertical distance between the top and the bottom of the paper is going to be negligible. So this is rho GV, okay, rho GH, okay, those terms are going to go away. And the only thing that we have going on here is there's like some difference in pressure that's due to the speed of the fluid on both sides. You can try this. Take a piece of paper, hold it below your mouth, and blow on it so the air goes across the paper really quickly, and the paper will lift up on its own. And this is the same principle of how a wing works. Okay, there's other complicating factors like dynamic lift and lots of other things. Okay, but basic idea behind first principle of how a wing works is that you shape the wing so that the air has to take a longer path over the top of the wing than the bottom of the wing. So if it's moving further in the same amount of time, it's moving faster. If it's moving faster, that kinetic energy density, that increase in kinetic energy density has to come from somewhere, and it gets taken away from the pressure at the top. Okay, the pressure at the top of the wing is less than it is on the bottom of the wing, because the air on the bottom of the wing is not moving as quickly. Okay, lots of examples in the textbook. Buoyant force, for Pascal's principle, buoyant force, equation of continuity. If you have any questions on any of those, I will be more than happy to make you a video covering any particular example you like. Just let me know.